All right, so I think it's now 2 minutes past, so we should be starting. So this is IPSECME working group starting. I'm Tero Kivinen, and my co-chair Joav is there in the just waving hello. So, okay, no, not that one. So, this is the note well. You should note it well. And there is, I have already one note taker who is taking notes outside the Etherpad, but if somebody else wants to take the notes in the, especially we need to have something about the discussion and questions and asked so on in the minutes. So if anybody wants to help with that would be useful. Anybody else volunteering? Okay, good. Just put it in the Etherpad and Peter will also fill up or whatever he gets on after he gets it done. So this is our agenda. I removed 5 minutes from some of the presentations to make it so that they actually fit in the slot we have. So you might have lost a couple of minutes somewhere. It's quite full, and we actually managed to get the slides just on time because I was just saying, okay, now I will remove this last press. Oh, damn, there's slides on in my email book. Any, bashing on the agenda? Okay, let's go forward. So we haven't published any RFCs since the last IETF. We have 3 documents now in the RFC editor queue. I think the rename ESN is now in out 48 hours, so it should be coming out in 48 hours, right? The author said that no, he can't do it while he's here, but it will come out very soon. I think the both GI version 2 and QR alt are in edit phase, if I remember correctly. We don't have anything that is publication requested yet, so the ADQ is empty. we don't have anything waiting for chairs to actually post, which is also or due to the several write-ups. We have 2 documents where we have a working group last call in progress, waiting for finishing touches for the diet stuff, which is actually old stuff from the previous charter, but they are still waiting for some input from SIG working group, and also I think that Daniel is still making one more edit out of those, and then we will probably go to the publication requested. We don't have any documents that will be ready for the last call yet, I think. Working group last call, I mean. We have multiple documents in work on process. I have no idea which one is actually going to be the main document of the ESP ping ones, because I think they were combined now, but I don't know actually which one is the one we should keep here, and which one is the one that it was merged. But and then we don't have currently any documents in the working group adoption calls, and I think Valerie will try to fix that.
Valery Smyslov, LS Plus. Actually, I requested issue an adoption call for at least 2 documents. It's reliable transport. That is very important for PQC staff. And now I have a Klaus Tiro, who also is very interested in this document, because when we send a large amount of data in IKE, it mostly needs TCP. And at the same time, we want to get high performance in ESP, so the transport should be able to be separated. And the other documents that I would like to issue adoption call for is a big payload by UAF. As draft is well known for a while, and actually it allows to transfer a large amount of data in IQ2 messages that might be helpful if we use some backup PQ algorithm like classic McAllister that doesn't fit into the IQ2 payloads. And I want to say that I have implementations. I've already implemented both of them, so perhaps it would help. And I also think that 2 more adoption calls but I will take during because they are related to the presentations that will be. I will later tell about them.
All right. So reliable transport and the big payloads was All right. I will. Is there anybody objecting of starting a working group? Adoption calls for those, because I think we have been discussing them earlier quite a lot, and they were people were interested on them earlier. Okay, I will see and issue an adoption course, and let's see if they are going to be adopted. All right, so then I think that was the end of the the document status, and we go to the presentation. I think the first one is EESP. Now I need to find this task slide control. Yes. Yes, it looks. Saves my work.
First time I'll do it myself. Yeah, hello. I'm going to give a quick update about enhanced ESP draft. So first, some history. First time we presented about that draft was at IETF 121. And here we basically presented about a packet format. We thought it's useful. We discussed the header fields and highlighted changes we plan to do to ESP. Then at the last IETF, we just took a step back. We explained why we actually think we need a new security protocol. We discussed the protocol design and the requirements we have to fit for our use cases. So now, in between, we got working group adoption and we updated the document one time. And so this time I just want to present on the updated package format and nothing else, because nothing else changed. And another thing is we now need feedback because we think the protocol as is ready to use. Okay, let's talk about the package format. So this is the top level of a package format of an EESP packet. we split the header in 3 parts. This is the base header, followed by the peer header, and an optional payload information header. And the rest of the packet is following then like it did on ESP. Yeah, this is how the base header is currently looking like. So it starts with 1 bit, what is set always to 1. This is actually new in this version. So we use this for implementations that implement eESP and ESP to distinguish the 2 protocols when we use UDP encapsulation, because if we have such a distinguisher, we don't need to have actually new ports for eESP. We can just use the same ports as ESP is using there. Then we have a version that's 4 bits. So whenever we want to do a major change to the protocol, we can bump the version and change the header on our needs. So that's hopefully quite handy. We have a flex field. This is 3 bits, where we actually use 1 bit for the packet format. I will talk about that later. And we have 2 bits reserved for future users. The next field is the uplength field. This describes the overall length of the options that can follow the base header. We have a 16-bit session ID that we use as a sequence number subspace ID to extend replay protection. We have the well-known SPI. And as already mentioned, we have options that are TLV encoded. The next thing is the peer header. This should look quite familiar. We have a sequence number and an IV on it. The sequence number is a little bit different to ESP, so it's optional, but if it's present, it's always 64 bits. So we do always ESN if we do replay protection. The IV, yeah, that is the same as for ESP. It depends on the algorithm and might be there or not. Yeah, the next thing is the payload info header. This is actually just required for transport mode, beat, and IPTFS. So what we did here, so eESP does not have a trailer anymore. So we took the next header field and the path length field from the trailer and placed that in front of the packet. And that's now carried in the payload info header. And we use this for transport mode and for beat because we cannot derive the next header or the path length field from the packet because we don't have this information here. This is different on tunnel mode. So for tunnel mode, we do not need to have this payload info header in place because all the information we need, we can just derive from the IPv4 or IPv6 header. So in that mode, it's left out, which is shown at the next slide. So these are the 2 formats we have. On one side, we have the full packet format, on the other, the optimized packet format. And if you look behind the IV, so for a full packet format, we have the payload information header there. And then it's following a layer 4 payload, just like transport mode or IPTFS. On the optimized packet format, it's different. We have behind the IV directly an IPv4 or an IPv6 datagram. So we can leave out the payload information header and we save 4 byte in that mode if we kind of decide to skip that header. Okay, so let's talk about options. I think I talked about that the last time too. So we just adapted the options from IPv6. So whenever an implementation can parse IPv6 header, extension header options, it can parse that one too. So it's quite flexible, so multiple options can follow the header. And so if future documents think we need some new options, it's easy to add those. So currently we define 3 options. That is the crypto offset, we have a flow identifier, and we have some padding as IPv6 had to. So crypto offset. As said, is a TLV. It starts with a type and a length, and then it has a field. This is called the payload offset. This tells you how deep in the packet the inner packet is actually starting. And then we have the crypto offset that tells you how many of the bytes at the beginning of the packets are not encrypted. And I don't want to talk about flags. This is things that we still have to do. So this is how it's looking like. At the top of the slide, we see a standard packet without crypto offset. Everything is as usual. Everything behind the peer header is encrypted as it is done in ESP. So below you see a packet with crypto offset. And here I choose a crypto offset in that way positive that the payload information header and the TCP header is shown. So middle boxes can parse on that. So we decide to have this crypto offset negotiable with IKE. So this is a different document where we define how the use of this crypto offset has to happen, but it's out of scope of the packet from a document here. Here we just show how it's happening in the packet. Okay, then we have a flow identifier option. This should carry some characteristic information of the inner flow. So the initial idea here was that we could just use that for intermediate devices to do eSMP or RSS, but in between the packet format evolved in a way that the session ID is kind of doing this now. So it lost this initial use case, but we think it's still could be interesting to have such a thing, so we left it in. So it could be used, for example, as an VNI, as Geneve is doing that. Here, and as said, we have padding. This is not that interesting. This is just to align the following headers as IPv6 is doing that too. Okay, and that's basically the thing. So let's just go over the major changes that we did to ESP. So first of all, we add the version number. So with that, we do not really need to ask for a new protocol number anymore, as we can adjust this protocol to our needs by bumping the version number. We added a base header at the beginning with a session ID that we plan to use for a sequence number subspace ID. We have TLV-based options possible. And so if we do replay protection, we transmit always 64-bit, but we have replay protection optional. This is negotiated by IKE. We have two package formats, as mentioned. We have the full and the optimized one. We removed all the implicit header parts. We removed the trailer, and we removed TFC padding in favor of IPTFS, because that's kind of a newer and more interesting thing to do. And last but not least, we restricted ourselves to AID only, to make things easier and to get rid of all the old algorithms that shouldn't be used anymore. Yeah, and that's the updates. So that's all I had. I'm open to questions.
Barry?
Sorry. Just a clarification, the related document, the ESP IQ2, is a little bit behind. So that ESP document was updated just before the IETF, so we haven't yet updated ESP IQ2. So Stephen says that this is negotiated via IQ2. It is not yet there, but it will be there. Just a clarification.
Yeah, that's true, and that's the reason why we don't present about that protocol this time, because we just didn't get it to update it. This will come the next time, then. Yes, right.
So I just have a question regarding the purpose of this document. Sorry, I didn't read fully in the document yet. But is that intention of this documentation to replace existing ESP? Or just complement?
Can you say it again?
Is the purpose of this document to replace existing ESP protocol?
Well, actually, no. I mean, we plan to have it ESP and EESP in parallel, but it could replace it in the future. But
I don't want to replace the ESP. I just don't make it that clear. Okay, I mean, okay, chances coexist, I'm fine.
Yeah, it can coexist, and the time will show whether it stays like that or not.
Hi, Stefan. A very quick clarification question. Does this kind of ESP closely or be mandatory bind to the IKE control plane protocol?
Well, so if we do IPSEC, then IKE should be used, of course, but we have in the document that you can use IKE or any other appropriate protocol. So if you think this protocol is handy for anything else, you can just take it and plumb the control plane, whatever you want.
I'm just a little worried because we have facing some use cases that it's because the IKE, the control plane negotiation is too complex or it has some delay. So we may want in some very special cases want to skip the IKE. So if ESP is closely bound with IKE, so it maybe not so helpful.
As I said, the document doesn't mandate to use IKE. So if we want to do IPSEC here, we usually do IKE, but it's up to you. You can use that protocol for whatever you want. It's just a packet format.
Okay, yeah, thank you.
Any other comments, questions? No? I think that's all for that. Okay. So I assume that we probably will be reading the document and sending more comments on the list. And I think I at least, we had actually several, comments coming up in the workshop already. And there is probably going to be some discussion about those.
Right. We had a 2.5 hours discussion last week. So yeah, so please read the document. So as authors think it is basically ready to use, so review is very welcome. Thank you.
All right. The next presentation is then SATS payload optional.
Hi everyone, my name is Weipan from Huawei, and today I'm going to talk about the optimized rekey in IKE version 2, and a brief background introduction is that in IKE version 2, when you do rekeys, actually when there is no configuration change and you don't need to renegotiate the parameters, for example, the key exchange methods. So in this case, you don't need to actually transfer this information in the rekey packets. So this is the idea of a draft. And currently, in the recent change, mainly include 2 points. First is we add some considerations about the interaction with the draft QRLT, how to use PBKs, and we have added a dedicated section 7.3, and we highlight that when you use this when the QRLT draft is used and support and used, and the use of PBKs must be renegotiated in the optimized rekey. You cannot just reuse the PBKs silently. And the other problem is about how to optimize the rekey for the initial child essay created in the IKE OS exchange. And the details will be described later. And the main point is that we now rely on the draft, this PFS info draft to solve the solve some of the problem. Yeah. First, the simple one about the interaction with the QRLT draft. Actually, we add in the section 5 how to do the optimizer rekey for child essays. We add some clarifications to say that when you use this QRLT draft, and then you will use the PBKs for the quantum safe. And when you do the rekeys, you cannot just silent. You must negotiate the PBKs and include this the negotiation payloads in the optimized rekey packet, and also have a dedicated section to describe this. And yeah, and the next point is about the initial child essay, and here is the first the problem recap. Because when you create the initial child essay in the IKE OS exchange, actually you don't need to, actually in the current RFC 7296, you don't exchange and negotiate the PFS policy and the key methods for the child essay. You just use the session keys from the IKSA to calculate the session keys. And here is a problem for the rekeying, because first maybe their two peers have mismatched configurations, and you will find out this when you do the rekey, and the rekey will fail. And the second problem is that if you do the rekey, you don't know actually what key methods you need to use, because it doesn't negotiate it before, and you cannot just guess whether the child essay will reuse the key methods of the IKSA. So you may guess wrong. So this is a problem. And last meeting we have discussed several solutions, but people may prefer simple solutions. And typically currently there are two choices. First, you can do just to try our optimized rekey, and maybe you will fail and just go back to use the regular rekey. But this is not feasible in the multiple KE situations, because according to RFC 9370, and if there is a mismatch of the KE methods in the follow-up KE, it would be a fatal error. So the whole IKE sessions should be teared down, and this is a very acceptable. It's not acceptable. And then the simple one is to use regular rekey for the first time, and then you can have the key methods be negotiated, and then for the next times you can use the optimizer rekey. But this solution is a bit sad to accept, because our goal is to avoid regular rekey as much as possible, and so there's no perfect solution. But the current situation is due to the fact that the PFS policy and the K methods are not negotiated. But what if they can be negotiated? And thanks to Valerie, he suggested a possible solution on the mailing list. It's trying to lift the prohibition of key transforms to be appeared in the SA payloads in IKOS exchange. And then you can negotiate the key methods for the child SA in the IKOS exchange, but you just don't need to use them for computing the session keys. And here the two pictures are some of the examples of the exchange. First, in the IKE UNIT SA, you just do the negotiation of whether you will support and use this this solution, and then in the IKOS you carry the KE methods transform in the SA payloads. And so this solution is very simple, and it's easy to implement. And we feel if this is used, we can solve the problem faced by the optimized rekey. And then according to this solution, we assume this solution will be used. We accordingly changed the draft, modified the draft. First, we add a dedicated section to describe how to do the rekey for the initial child essay. And in this, we highlight that we need to use the solution defined in the draft, the PFS in 4. And if this draft is used, the solution is used, we can use optimizer rekey. And if it's not used, we need to use the implementation should use the regular rekey the first time, and the optimizer rekey for the next times. And some problems is that it will cause dependencies between these two drafts. This optimized rekey will normatively relies on the solution, and the problem is, well, the draft PFS info adopted the solution on the previous page, and where the working group adopt the draft, and yeah, that's some problem. Let's say end, and yeah, do any guy have thoughts about this, and we need more future tests? Yeah.
Paul.
Hi. Paul Valkos, no hats, but actually, sorry, co-author hat. I think this document is ready for working with last call. Valerie and I have already sort of committed to cranking out the fix in the other draft really quickly, so hopefully we can get it out in the next 2 weeks and then get an adoption call for that as well. So I think the waiting on the other document is not going to be a big problem. I would like, though, even if we do a working with last call for this document, I would like to see actually 2 independent implementations, especially with the QR alt draft interactions, to just make sure that we didn't forget any corner cases.
Yeah. Okay.
Right. So that's all for that. Then next one is ESP ping, ping, ping. No response. Okay, next one.
So this is I'm going to give an update about 2 drafts, because eventually we are going to merge them into 1 draft. So these are the 2 drafts. It is initially the unencrypted ping and the encrypted ping. Oh, sorry. So since the IETF 121, these 2 documents got adopted. And the consensus we reached between the 2 drafts is both pings will have one common format, and the unencrypted one will use the format which is defined in the encrypted one. And the encrypted ping may additionally support more formats, which is borrowing from the IPTF's congestion control payloads, and that can do more things. But in the unencrypted one, we don't need any of those. We just need a basic packet format to see the reachability. Because it's unencrypted, you cannot put any data in there. And so we hope to make our implementation during the hackathon, but we got distracted with some performance things. So performance tests, and so the current idea is to go back and merge the document and come back and try an implementation. So there were some interesting ideas we discussed how to implement them. So the current thought is, instead of the ESP layer responding to the responses, the whole data being request will be given to the IKE daemon, and IKE daemon will send the response back to the ESP, and then ESP will packetize with the right sequence number and send it back. That's it from the updates. If there are any specific questions for these 2, I'll take them. Okay, going to my next presentation. The next draft I'm working on is a IKE v2 beat mode. So this was a working group adopted since the IETF 122. So the next goal on this draft is to get a IKE v2 negotiation use beat mode code points. Once we have it, we can keep using the existing beat format, which is defined in the appendix B of the RFC 7402. And simultaneously, we also propose to write a new draft to take out this just appendix and create a packet format RFC which just defines the ESP beat mode instead of hiding it in the RFC 7402, which is a HIP RFC. So that's all on that one. If you have any questions.
No
I
comments.
save a lot of time for the chairs.
All right, I luckily take 5 minutes off from your presentation already, and you did it in 5 minutes faster than you were supposed to. So next one is downgrade, which I think we probably are not going to get faster than.
Hello again. So first of all, full disclaimer, the slides are prepared by Chris, and the whole discussion was initiated by him. So I'm here just a presenter on the talking head, and one of those who proposed a solution to the problem. So I hope that Chris is listening. If I forget to say something or say something wrong, I hope he will pop up and correct me. Okay. Actually, we ran into some problem. We don't know how severe it is, but we found that IQ2 is susceptible to some kind of downgrade attacks with pretty complex preconditions that are perhaps not very realistic, but still can happen in some situations. If initiator and responder have a policy that allows them to use weak key exchange method and strong key exchange methods, and if an attacker is able to break weak key exchange method in real time, and if an attacker can forge an authentication information of one of the peers, at least one of the peers. For example, his key is compromised, or he can, I don't know, forge the signature, then an attacker is able to force both peers to use a weak key exchange method instead of strong key exchange method. And in this case, an attacker can eavesdrop what peers are exchanged. So actually, it's very interesting attack because it's active attack, but its purpose is not active. Since attacker has compromised a long-term authentication key, it can impersonate this person, but it is not interesting for the attacker, because if it impersonates this person, it doesn't know anything new, what this person would talk to to its peer. So the goal of attack is passive, but the attack is active. So the details. So there are several variants of this attack. It can be mounted of a pure classic key exchange method, or it can be mounted in situation when peers can do hybrid post-quantum key exchange, but also can do the configurations allow them also do only classic key exchange method, and in situation when attacker can break classic key exchange method, for example, by means of quantum computing, it can mount a downgrade attack. So there are some mitigations possible, and the most simple mitigations is just allow only strong key exchange methods. It's very simple mitigation, but not always possible in practice, because for some deployment reasons, it can be desirable. It's not only in all situations, not in all situations, peer know beforehand that the peer they want to connect to supports only strong key exchange methods. So, and it is also possible to prevent this downgrade on a protocol level. And this is what draft IPSECME IQ2 downgrade protection proposes. So go to the details. So preconditions. An attacker is on the path. It can read all the messages and can modify all the messages that initiated and responder exchange. Both parties, they prefer, I will talk about the kind of attack, the type of attack that is concerned with post-quantum hybrid key exchange. Because as I said, there are a set of different attacks that can be mounted. This is most, I don't know, understandable, one of the most simple to understand. So both parties prefer post-quantum key exchange, but they can fall back to only classic key exchange methods if they cannot negotiate, if they, during negotiations, they understand the peer doesn't support hybrid post-quantum key exchange. And also attacker can compromise one of the party signing key. There is also possible attack when attacker compromise not this particular peer's public key, private key, but private key of another peer. So it is a combination. I will talk a little bit further about this. It's a more strong attack when downgrade is combined with unknown key share. So Paul, do you want to ask?
A clarifying question, yeah. When you say signing key, like, are you talking about the auth payload signing key?
Yes.
But that in itself could also be a hybrid, right?
Hybrid only key exchange. And we're talking
sorry. If, like, for instance, if you have XOR certificates and those certificates are either hybrid or you do dual certificates.
In this case, an attacker can compromise this hybrid key too. Somehow it's still your token and knows your post-quantum hybrid private key, signing key.
Right, okay. And then my second question is, this is only for the initial exchange, right? This does not apply for rekey. So if you have a long distance connection...
It's only for authentication. Okay. So it's for initial exchange only. Next. So what is the source vulnerability? So this is just how IQ2 works. So we have IKSA init, IK intermediate, I mean with hybrid post-quantum key exchange, and IK both. And so each party only signs its own IKSA init message. And the blob that each party signs is constructed that it starts with its own IKSA init message, peers nonce, and MAC with its own ID and session key. For example, let's consider a situation when how post-quantum key exchange is working in IQ2. So we have two proposals configured for both on both peers. First is P256 only, and the other hybrid P56 with MLGAN. And so initiator sends both proposals. Responder selects the stronger one because it's a natural policy. Then they exchange MLGAN. Then they generate authentication information. And when they generate the authentication information in IKE auth payload, each party only signs IKSA init message that each sends, and not the IKSA init message it received. So this allows an attacker to modify. So each attacker in the past can modify messages. And this attacker just removes the proposal with hybrid key exchange method from the IKSA init message. And then what next? When it comes to signing, an attacker who can decrypt, who can break the traditional P266 in real time, so it can learn all the session keys, it can modify IQOS messages, it can read them and modify. And since the attacker also compromised initiator's sign-in key, it can change the auth payload. So as if initiator just sends only proposal with traditional key exchange method and not with post-quantum. Paul?
This seems like a lot of hard work for the attacker. Why not the attacker with, you know, let's say I have the keys to your laptop and you're asleep and your laptop is asleep. I just start an IKE connection to the responder and I only do my classic algorithm and I don't need to hack anything. I'm just your original client.
Yes, but in this case, you as an attacker, you impersonates you. But this is not goal of attacker. I can impersonate you, but I cannot know what you want to tell to responder.
Sure. I mean, there's a small difference between eavesdropping on the connection and just being the client yourself and having to extract whatever's on the responder, but
no, because if you don't modify IKSA init messages, you cannot. They will use hybrid post-quantum key exchange, and you cannot break it.
No, but I can still, as a client, independently set up the same tunnel as if I'm the initiator by just using classic algorithms with a fresh connection. I don't need to break your connection if the goal is to just reach the responder as you.
But client won't use only classical key exchange method in normal situation. It will insist, client actually insist on using hybrid key exchange. But an attacker forces client
But if you were insisting on a post-quantum algorithm, this couldn't happen either.
Yes,
so you are
I
already
understand.
allowing.
Yes. The policy is that allows both to use only classic key exchange. That's of course that's the reason the attacker succeeds. It is possible for them, but in normal situations they will use hybrid key exchange because it's more secure. They use.
I understand that part, but I don't. I guess I'm somewhat failing to recognize why should we defend against a situation where I have your signing key and I can just pretend to be you anyway. And then I can actually still use post-quantum algorithms as well, right? I can still connect to the responder with post-quantum algorithms if I've got your signing keys.
I don't think so. Well, okay, we can discuss on the list.
Thiru Nokia. I see in this case the attacker has access to the signing keys, right? So either it can act as an MITM, right, man-in-the-middle attacker, or it could just act as a transparent proxy, right, just to eavesdrop and see what's happening without tampering any of the messages. So in both cases, the attacker doesn't have to degrade what's happening, right? It can continue to support the same PQ levels and still have visibility by acting as an active proxy, right? As one of the peers, right? So it cannot be detected by both the peers because they would be thinking I'm talking to a legitimate peer, but you would be interacting with an attacker who would be just seeing all the traffic and still using the right crypto combination of.
It cannot be a proxy. It cannot be a proxy because it cannot authenticate. It cannot act as a responder authentication to attacker, to initiator. So it only has initiator signing key. It doesn't have responders signing key. So if initiator, so as a proxy, you cannot authenticate that you are a legitimate responder to initiator. It will not set connection with you. So the prerequisite that attacker has only one signing key, initiator. It doesn't have responder signing key, so it cannot be a proxy in this case. Okay, so next one. Okay. Chris?
Oh, sorry. I thought you were saying next slide. Yeah, so to kind of clarify that point, the way I think of this attack scenario is, I've compromised the initiator signing key, and then I see it, come online and start talking to the responder. I can then kind of the idea is that without being noticed, I could downgrade that connection and then start decrypting the traffic. So I think that's a legitimate form of an attack, but I sort of agree that it's a little hard to motivate. The next slide is going to present a stronger attack, where the victim initiator is not actually like, you don't have to compromise anybody's signing key. You can just be an initiator that the responder is configured to trust. So so before we dive too deep into kind of critiquing this particular threat model, the high level thing is you can strengthen this attack, and it might be possible to strengthen it even further if we don't have downgrade protection. So that's all I want to say right now.
Tomichas, I just wanted to quickly add that in sort of the key exchange literature, we would call this a key compromise impersonation attack. So there is lots of precedent for these kinds of attacks on protocols. This is not whether it actually is something that is practically something problematic is separate, but this would break like the usual ways that you would analyze a protocol on paper, at least.
Okay, so no one is queue, so continue. Okay, it is possible to prevent this attack if both initiator and ICAS init request and ICAS init response messages are signed by both parties. So in this case, the attack will be detected. has access. I've seen it. Okay. It's possible the more strong attack if attackers can access not the initiated, has access not to the initiated public key, but to some trusted parties, trusted for responding public key. So in this case, it is a combination of downgrade attack and unknown key share attack, because actually in this case, responder thinks that it established a connection with someone and not with initiators that really established this connection. So mitigation. So the easiest way to completely mitigate this attack is just disallow weak key exchange method. In this case, it's disallow only traditional key exchange method and always insist on hybrid key exchange. Is this particular version of attack. It's very simple, it works, but it is not always possible in real life if we are talking about incremental deployment, and if we are talking about cases when initiator and responder doesn't know beforehand what they are talking, whom they are talking with. So, for example, consider situations when Alice, as initiator, want to get a loan from several banks, and she established a secure connection with each bank, but each bank has its own configuration, so Alice doesn't know whether it is not a corporate VPN. It must support both post-quantum hybrid method and traditional key exchange method, but in each case, it sends some valuable information about her application to a loan. So an attacker can force even bank supports more stronger key exchange method. Attacker can downgrade this information, learn something interesting about Alice. And option 2 is add protection in the protocol level. So Paul?
Yeah, just go back one slide, sorry. So I think what we should really do is take a step back and say, it's not just about a downgrade prevention here. What we're really trying to avoid is that the two parties think that they have agreed something, but they both reach different conclusions. So generically that is bad, and generically that should be fixed, whether it is one auth payload or whether it's like a notify payload that came in. Like in general, we really want a cryptographic proof that both parties have reached the exact same state of what they think each party has done and sent and received. So it's more than just a downgrade attack, I think. I think it applies more generally. And I think it happens to be that your solution probably actually fixes it more generically. But I think the problem is a more bigger generic problem.
I think I agree. And at the protocol level, okay. Julian?
Okay, thank you. So actually, I would like to say, these two reasons are definitely valid. But I would like to say also as well, I mentioned in mailing list. So because the reason to select or algorithm can be selected is weak, not just because post-quantum or quantum threat, could be some other reasons. Like the attacker just have an advantage because he supports some flawed implementation, even it is on a post-quantum algorithm, KEM. It could also be. So the meaning of weak here is not really about the normal understanding of a security level. It could just from the viewpoint of the attacker, in some way.
Scott.
Scott Fleur, Cisco Systems. From what I hear, it sounds like a presumption of both of these attacks is that the attacker has access to a valid signature private key.
Yes.
If he does, there are already some impersonation attacks which cannot possibly be avoided because the attacker,
But it is not interesting to impersonate for an attacker. It is interesting to get some information that initiator will send to the responder. If an attacker impersonates initiator, it doesn't have this information. So as I said, the attack is really active But the goal of the attack is eavesdropping. The goal is to get some passive eavesdropping of what they're talking about.
Yeah. Unless the fix is very easy, I think that the moral of the story should be keep your signature keys safe. Otherwise, you do not have security.
Jim?
Yeah. So one comment regarding the con you list here for the option 1. You said sacrifice connectivity with the legacy peer. By legacy peer, I assume you mean that the peer only supports like weak diffie-Hellman, right?
Yes.
So, I mean, if a client only supported weak diffie-Hellman, and nothing we can do here. I mean, when
If
the
it
computer come around, regardless what your protocol change you're proposing here, doesn't help it, right? So I think the only problem that we're trying to prevent here is that we're trying to prevent two peers, both has capability, supports strong diffie-Hellman, but somehow be changed to use weak diffie-Hellman, right? That's what case we're trying to prevent here. I've been doing IPSEC for more than 15 years. All deployment I have seen, that at least one side will know what's the capability of the other side, if not both sides know each other. So I think this problem could be easily addressed by the configuration.
Yes, but what won't I say? It's easy to mitigate reconfiguration. I know, but if it is prevented at protocol level, that we can forget about all mistakes with configuration, about all the cases when incremental deployment, all the cases. Configuration is a good idea, but I understand that
sure.
On the protocol level, it's always better.
Yeah, that I agree. I agree. If IPv2 design from day one, that like what you propose here, I'm very happy. But now IPv2 is implemented, like deployed everywhere in the world. We are proposing some changes to IPv2 protocol to address something could be easily addressed by the proper configuration. And I would say there's nothing we can do to prevent people doing dumb things. I mean, people do dumb things all the time, and there's nothing technically we can do to prevent people doing that. So I'm just saying, let's say even you working group decide to go with this draft, or then I would just suggest at least adding some text in there says this could be mitigated by the proper configuration.
Yes, it could.
Alicia Cario, Red Hat. So I think the confusion stems from the fact that you compared it to logjam, while in actuality, I think what you're describing is the free handshake attack on TLS. And the solution to that was to use extended master secret, which tells, yes, we are hashing all the handshake messages to the secret that is then used for deriving the authentication keys and encryption keys. So I think that's basically the same thing that we should do.
This is, well, I don't know whether it's the same, but actually the draft downgrade prevention just suggests to add in both initial message to transcript, so that both are signed. So this attack is not possible. You cannot modify those messages anymore.
Yes, but like the reason why it was added to TLS and basically became essential part of TLS 1.3 was to address the whole scope of like the whole area of this kind of attacks where you have peers that where one side thinks that it has negotiated one set of algorithms, while the other thinks that we actually were negotiating something completely different. So the solution is to that they both need to agree on the whole handshake transcript before the.
Yes, that's what's suggested in the draft, actually. So the draft just overrides authentication logic by adding both initial message instead of only its own authentication message, message to our authentication blob. And this is also, the draft is also written in such a way that if both peers support this logic, then an attacker cannot persuade them that it is not supported by one of them, it will be detected. So it is not strict negotiation. As in IPv2, we always do a negotiation that initiator sends some notification payload, and only if responder sees this response in the request, it responds with the same notification payload, acknowledging that it supports some extension, like IPv2 extension. And this draft, it is done a little bit different. So each pattern conditionally sends a notification saying that I can do this downgrade prevention IPv2 extension. And since with the current IPv2 logic, at least the own message is always signed by the sender. If an attacker modifies either IKC init message request or IKC init response, it will be detected. So it cannot force peers to not use this extension if they support it. And extension itself is very simple. It's very easy to implement. It's a couple lines of code in almost every implementation because both request and response messages are retained till ICALL's exchange. They are already available. And you just need to check one flag and just sign both of them. So I think that's all. And the question, should we add protection against this attack to the protocol level by adopting this draft, or should we rely only on configuration?
Chris, you're first in queue.
So thanks everybody for listening. I just wanted to, I think a few people articulated in the queue exactly what we want. It is more general than downgrade attacks. Really, the goal, like the goal that we want for the protocol to achieve is that the peers agree that they've had the same conversation, and there's a lot of benefits that fall out of that, not just prevention of these attacks. So I think the feedback that I think people in this room who have deployment experience with IPSEC should look at this and actually make sure this is what the protocol does. But that is exactly what the extension's goal is. The other thing I wanted to say about just to clarify about the threat model. Valerie presented like two variants, one where I've compromised the victim initiator or victim responder's signing key. The second variant doesn't require compromise. So I can be any old, so if you have the responder that is configured to talk to two initiators, call them I and call them A for the attacker. The attacker can do this, can mount this attack against the connection initiated by the victim initiator. So it doesn't require key compromise is kind of the high level message. And this attack's been known about for a while. Like there was a variant described in a pretty old paper from around the time TLS 1.3 was being standardized. And we should expect there to be stronger variants. So I think it's something. It's not just about PQ. This is it's something that I think IKEv2 would benefit a lot from as it continues to evolve.
Valvout's individual. Yes, I agree. Can you go back one slide just for clarity? So the first sentence says, right, signs the entire auth exchange message. I think just for everybody in the room, that all the messages leading up to this have already been hashed into the key material generator. So it's not just that we have hashing the auth message, but we now have then successfully hashed every message in the entire exchange, right? It's just that we didn't hash the auth in the final part. And now you're saying, let's also hash auth in the final part, right?
I don't know. With regard, I can only say that with regard to intermediate, we are safe because they are added to ICALL's calculation, and both request and response.
Oh, I see.
You cannot do anything with intermediate.
You're saying because we're starting IKC init with the classical algorithm,
yes.
That would be an additional.
Only IKC.
Okay, I see what you mean. But okay. Yeah. So we. So the question is, can you do anything in IKSA in it that would
Yes.
be that would be problematic? Yes. But otherwise, it would be really expensive anti-DDoS cookie.
So actually, I have one question. How can actually assign the entire IK out, because you are including the IK out in?
I'm not talking about ICOs. It's always talking.
Oh, but you said that the entire IK out exchange.
Where?
Or is it supposed? I was assuming earlier that you were supposing that we are actually assigning the IPSECME init.
I think it's a typo. It's a typo. It's my
There's a typo on the slide. I'm sorry.
IPSECME. Yes.
So now we.
Thank you for noticing.
Yeah. So now we are signing.
Yes.
Currently, we are signing. IKSA init from our end.
Yes.
And and now we added two real messages.
Yes.
1 and 2.
Two real messages. Yes. So
I think that was explanation about that. I think we should be probably taking that to the list and continue the discussion there, because I think that this is a good discussion here. People.
It was already a lot of discussion of the draft.
Yeah.
So perhaps we just make adoption call. I don't know.
I don't know. I think I want to have actually more discussion on the list. Even if, because I don't know if everybody actually understand what they are reading the draft. It was I haven't read the draft, so I just don't know from presentation. I think there's also other people. But let's go to the next one. Or do you have this still on this?
Yeah, just one comment that if you could update the draft with an attack which doesn't involve key compromise, I think that will make it quite clear to help everyone support it, right? I mean the case that Christopher was talking about.
Oh, so the draft doesn't include that one?
Yeah, it doesn't discuss.
Draft doesn't include the one that has the key compromise, without the key compromise. I agree that the one that when somebody's key is compromised, I think that is, you are already mostly lost in that case.
Yeah, so if that other scenario is discussed, that would be really helpful.
All right.
Yeah, for what it's worth, just stating for the record, in the Zulip, there is tons of support for an adoption call. But yeah, I agree that attack should be described in the draft.
Okay, we good to go?
Yep, go.
Oh, good, the clicker works. Okay, hi everyone. This is an update on a draft we originally presented in Dublin. Since then, we've changed a few things, we've removed a few things, so here is the new version. So, as led by the title, this draft is aiming to specify KMAC as a PRF and as an integrity algorithm used to protect IKE and IPsec security associations. And we're also looking to specify SHA-3 and SHAKE as hash functions used in the digital signature authentication method. So to motivate why you might want to use SHA-3, here's a few possible reasons. The first most obvious reason is its insurance against any potential future weakness in SHA-2. I think SHA-2 is fine. I think it's going to be fine for a while. It's not going anywhere. But if something bad happens to it, it would be nice to have SHA-3 in our back pocket. Perhaps a more compelling reason is if you're building a post-quantum IPsec implementation and you want to use the NIST post-quantum algorithms, so that's MLChem or MLDSA, they have SHAKE built into them. And so you need to have a SHAKE implementation in your crypt library if you're using them. If you want to build a small implementation of IPsec with a minimal cryptographic surface area, you might want to therefore use SHAKE or SHA-3 everywhere so that you can rip SHA-2 out of it entirely. So that's another good reason for using SHA-3. And finally, I think they're sort of the nice way of doing things. If you use KMAC, it's an extendable output function. This is a more modern way of doing key expansion. And I suspect if we were designing IKE v3 now, we would look to be using something like KMAC, like an XOF, rather than the existing method. So to be a bit more specific, this is what the draft specifies. We are including two variants of KMAC for the auth transforms, so KMAC 128 and 256, and the same variants for the PRF transforms. This means that when you call PRF+, this can become a single call to the underlying KMAC XOF, rather than having to repeatedly call SHA-3, which is what we currently have to do with SHA-2. This is a bit of an efficiency boost. I'll go into a little bit more detail on that in a couple of slides' time. We're also looking to put the 3 forms of SHA-3 and 2 forms of shake for the digital signature method. Paul, do you want to come up now?
Yes, Paul Wouters, no hats. Why would you want it for auth? Why would you want an auth KMAC? Because auth is only used if you do a separate encryption and integrity, like a pre-AAD. Why would you want to do SHA-3 with any kind of pre-AAD algorithm?
So I agree. If you're using an AAD, great. It sort of feels like if you're adding it already in for the PRF, it almost makes sense to add it in for the auth. We mainly want it for the PRF personally. If there are implementations that have separation of encryption and authentication built in, then they could use this. I'm not aware of them necessarily.
As a software vendor implementer, I would like to not have extra bells and whistles where I can avoid them. So I definitely do not want my customer to accidentally use SHA-3 for some AES CBC algorithm or something.
That's entirely reasonable, yeah. If that's what the working group wants, we can remove it. The main reason we want it is for the PRF, to be honest. Hello? So when we presented this in Dublin, we'd also included HMAC SHA-3. We saw this as a bit of a drop-in replacement. So if you're using HMAC SHA-2 in places, you can cross out the 2, write in a 3, migration done. The general vibe in the room was that HMAC SHA-3 is a slightly weird construction. Why would you use it? You should instead just use KMAC. We have therefore removed all of the HMAC SHA-3s from this draft for now. Yuri, do you want to get up to the mic?
Just a quick one. First of all, kudos on removing HMAC with SHA-3. It's cryptographically unnecessary. Second, one of the arguments you made, smaller library, that would apply only to software implementations. Because if you implement in FPGA, then it would not matter. You would be unable to reuse, most likely.
Okay. The implementations we're thinking about are software implementations. If you care about hardware, you may not wish to implement this. So yes, we've removed HMAC SHA-3. Yay. So there's a couple of remaining open questions. And as I see it, we don't need to answer these questions before we go for adoption, which is something we'd like to do. These are something that can be hashed out by the working group, but I will display them now. The first question is how to do PRF plus with a variable length output PRF. So just to recap, PRF plus is essentially HKDF expand. It's a way of calling the PRF multiple times to get more and more key to do key expansion. And all existing PRFs in IKE and IPSEC are fixed length. So it's sort of, you just call HKDF expand in the obvious way. But with KMAC, we don't need to do this because it's variable length output. We can just get all of our key at once. So what's the best way of fitting this variable length thing in a fixed length hole? So on the left, we have the kind of API for PRF plus. We've got these K and S inputs, which we normally pass in. And there's this L, which is the length. In RFC 7296, this is implicit, but I've made it explicit here because in our definition, we need to pass this length field into the underlying PRF, which in this case is KMAC, in order to get the correct output length. We've also got this 0, 1 on the end of the definition of concatenated to S, rather. We've included this because this makes it sort of as consistent as possible with the current PRF plus definition. As I say, this is a bit like HKDF expand, and this 0, 1 is essentially a counter, but because you're only doing one iteration, it's just always 1. Yeah, this is sort of consistent with PRF plus, but you would have to make some tweak internally to pass this length field into the underlying KMAC function. This isn't the only way of doing it. This is the way we came up with, but there are other ways you could do this. So Valerie's written a draft which aims to solve this problem of variable length outputs more generally. And his draft has this second construction, which is simpler. It just takes the inputs to PRF plus and sticks them straight into PRF. This doesn't look as consistent with the existing PRF plus definition, but if you're already tweaking with the innards of PRF to pass this length field in, maybe the right thing to do is just to do something simpler. I'm not sure. Something for the working group to decide. One observation here is that if you call PRF plus and PRF with the same inputs, you get the same output. So the output isn't necessarily bound to the context in which it's called. I'm not really a cryptographer. I don't know if that's a problem. I'm sure there'll be other people in the room who have stronger views on that. Valerie, do you want to get to the mic now?
Valery Smyslov. I just want to make some, I don't know, preference. Well, actually, I'm not, I don't insist that context strings are empty. It's up to cryptographer to decide if they're essential, let them be. My thought is that I think that it must be generic to all class of variable output size PRF functions and not to KMake only. So I think that it should be defined. Well, first I think that draft PRF plus should be adopted too and should define just a generic rules for such class of PRF functions. Currently, we have only one example of such PRF functions, well known, it's KMake. But who knows, tomorrow another function will appear, so it's better not to have a separate context string. And well, it's better to specify generic thing in generic draft. That's why I think that PRF plus should be adopted and all the generic stuff should be there. And SHA-3 should also be adopted, but just reference this draft for all this stuff.
Absolutely. I'm very glad you said that because that was probably our desired outcome, was for the generic draft to kind of define the mechanism, and the SHA-3 draft basically lean on that. Obviously, we will need to choose which mechanism to have. On the subject of context strings, I do actually have a whole slide on it. So KMake supports using these customization strings, which get hashed into the hash context when you call it, and it essentially binds the output of KMake to the context in which it is invoked. We have 4 customization strings for the 4 contexts in which you might call PRF, when it's in the PRF, when it's in PRF plus, and when it's protecting IKE and IPSEC security associations. We've currently specified them. There's a question around whether we want them. No IPSEC PRF or authentication algorithm currently uses customization strings, so this would be a sort of new thing, but they're there for KMake. I think it would be good to use them. It's something for the working group to decide, I think. That is all I had. As I say, yeah, we're hoping to get adopted, and then we can hash out these problems on lists and in future meetings. Yuri.
I would call them domain separators and would say absolutely yes. They would cost nothing. I didn't analyze, so I cannot tell how much good they will do. Likely they will, so.
Yeah, this is our thought as well. We haven't analyzed how bad it is without them, so we sort of want them. The only issue is whether it's awkward to include them because they're not used currently anywhere, but yeah, agreed with you. I don't know who's next in the queue.
Adam, I think.
Yeah, so I'm Adam from the UK National Cybersecurity Centre. I'm one of the co-authors on the draft. There was a point earlier about integrity for HMAC, sorry, not HMAC, KMake. I think the reason for that was for ESP null, so if you want to do integrity only, but kind of as the authors aren't particularly keen on including it, if there's no strong use case for that.
Yeah, it's a big if you want to do ESP null. Thank you.
Quindang at NIST. So Shake right now, in the case that people don't need to be FIPS compliant or anything like that, then Shake, the use of Shake will be fine. Very good choice. Unfortunately, right now, Shake is not a NIST approved function where which you can use anywhere. So only SHA-3 and KMake are the one really approved for use in protocols and applications. However, if we ignore FIPS, compliance for now, and we just want the best protocol design, then I would go with the Shake only, and I would be able to work with with the group or with the co-authors of the draft to specify a really nice way of using Shake for IKE and IPSEC here. So then we don't need to do like SHA-3 and KMAC and 2 different functions. So a Shake alone would be able to do everything in the protocol. And also there would be supports all the post-quantum currently being used right now. So that would be really nice. The only technical would be the FIPS compliant one. But if that is adopted and be widely used, and I think we would take a really good look at that and consider whether or not to prove it. And if there is no security problems that can be seen from review, then I think it would be a good chance that NIST would happy to approve it. But I'm not, the decider for that.
Sure.
But on technical matters, I think that is possible. So from the group perspective, I think maybe want to go to design a really elegant protocol based on Shake alone. Okay. And I would be able to help with that.
We'd certainly be happy to take
to help with that.
Yeah. I'll talk to you afterwards.
Yeah. Okay.
John Matson, Ericsson, thanks for doing this. I think we should adopt this. I think we should specify the use of Shake in all protocols as an option. I think we can adopt this now and discuss whether to use context or not later. I think FIPS compliance should maybe not be an issue if this is, as Quinn said, FIPS can be updated later to include this. Let's do the best protocol design possible.
Okay, thanks.
My question is for NIST. I missed part of the discussion. Is NIST considering, or would NIST consider adopting Shake?
Quinn, I think that's one for you.
If so, would any action of, say, this working group be required for NIST to do so?
Very shortly.
So, Quintang, again, just one example, like the ML-Chem and ML-DSA and 3 other parameter sets with SLH-DSA with Shakes. So they're all based on a Shake, even though Shake was not and is not a proved general use function, but we proved it because that was the right thing to do, and we did that. But again, I don't have the decision making on this matter. But generally, if there is a wide use case and we've been requested to review it, then we would do it, and then we would make the decision based on the result from our review. So it's that's how it works. And so in that case, when the protocol is well defined and be deployed, and then at the other time, some vendor, some user request NIST to take a look at it, review the proof of Shake, then NIST would do a review and then make a decision later.
Cool. Thanks, everyone. You will hear from me on the list.
Okay, so we are now about 20 minutes behind the schedule. So which means that we are going to be probably dropping one of the presentations at the end. So be very quick and short questions and comments. Right.
Okay, thank you. So I first present this draft in Dublin. This is the second time. I cannot skip this one. I guess everybody in this room understand what hybrid authentication in quantum computing means. So I don't think there's enough discussion in the main list around how do we want to go about this. So I want to reiterate the design choice I made in this draft. So first, in my draft, I'm reusing the OS payload format as a digital signature format. I'm not changing anything of that, just need a new auth method value. Second, that for the reason of efficiency, instead of using multiple authentication exchange, I decide to use a single exchange for authentication for both composite certificate and also dual certificate scenario. And also because of that, I want to always using composite signature for both a separate certificate and a single certificate scenario just to avoid event view, and also consistent with the certification verification process, because for IQE2, in addition to verify the auth payload, the signature generated by the IQE2 peers, but also we have to do the certificate chain verification using normal standard PKI method to verify up to the trust anchors. And lastly, I extend the supported auth method to advise what kind of the authentication, like hybrid authentication combination that you support. So basically, that's the 4 choice I made. So essentially, what's changed, what payload changed out by this draft is one that I need a new support auth method format to list all those login IDs that are defined by the other LAMP draft. And also, I want to have a new auth method value. There's no change to the auth payload or the certificate payload. And in my draft, I named this 2 type of the CA setup. Type 1 is basically using a single pair for certificate and keys, that using the composite schema specified by the LAMP draft. Type 2 is essentially using 2 pairs of certificate keys specified by the other draft in the LAMPs, RFC. So I think both, are valid options in IETF to pursue with how do we migrate to post-quantum hybrid signature schema. I think we need to support both for the IPSEC application. And ideally, I prefer to use a single solution instead of 2 solutions for these 2 type of setups, because essentially it's the same problem, just 2 variant. So another choice made, I said I don't want to use multiple auth exchange, which is RFC 4739 for the separate certificate setup. First, the reason I want a single solution for both these scenarios. Second, I want to minimize the number of exchange, given it's already quite a lot, given that this hybrid authentication will very likely to be used together with hybrid key exchange. So if you take a look at how many exchange we need for the hybrid key exchange, that's already adding a lot in current 4 message exchanges. So I want to minimize the number of exchanges that we need to set up the IPSEC tunnel. I understand from list discussion that there's concern that this will increase the package size, because now you are adding, for example, in type 2, when you have separate certificates, you need to have 2 certificates in the same packets. Of course, it's a much bigger compared to the separate authentication exchange. But my argument here is that even we do using separate authentication exchanges, those packet sizes will be already big enough to cause fragmentation already. So you are not avoiding fragmentation. Second, I would think that compared to my approach, which is a single authentication exchange with 2x of fragments, is simpler and more efficient than you have 2 rounds of authentication exchange with 1x fragments each. I think that this single exchange is more efficient. So another point is that why do you want to use the LAMP draft, the composite signature, to generate and verify the signature in auth payload? So I mentioned this before, that we need to verify the certification anyway up to the trust anchor. So I don't see point having a different mechanism to do the auth payload signature generation and the verification. So we just follow whatever the LAMP decides, and we do the same. Another concern is that with hybrid authentication is that key reuse, right? This applies to both scenarios. It basically means that the component keys, it cannot be used for any other purpose besides for example, IPv2 authentication. So here, in my draft, I designate a fixed IPv2 specific context for this purpose. So if you read the LAMPS draft, there's a signature process and the verification process. There's a one explicit input of context. So in that context, I use the IPv2-PQD-hybrid auth as a context, so that make sure that to mitigate that key reuse issues. And lastly, I mean, this just changing the version 2. I just at the time of writing version 2, which is back in I think in April. So that's when the LAMPS draft is still in the version 4. So I align with that. And apparently now they have made more breaking changes along the way. Now it's like the latest version is version 7. So I think the idea here, whatever that they do, we'll just follow them. I mean, it's just how we generate the auth payload and the verified auth payload. And that's it. Question or comments? Scott.
Scott Fluor. I believe in your type 2, each peer will need to get 2 certificates. That means, as I understand it, a change in the IPv2 protocol where you pass only 1.
No, IPv2 protocol allow you to have multiple certificates. Mm-hmm. Today we only allow 1 identity certificate, and then you can have like an optional CA certificate as well.
Okay.
So I would just suggest being careful about the key reuse argument. So if you look closely at that draft, it sort of acknowledges that it provides some protection for like kind of weak cross-protocol attacks, but it's not going to provide protection in all contexts. It's much better if you could just avoid key reuse altogether.
Yeah. So in my draft, in this security consideration, I specify that you must not reuse the same key for other purpose besides the IPv2 authentication.
Okay.
So Valery Smyslov, can you please go back a little bit with 2 options, type 1 and type 2? Oh, okay. And there was a discussion at the TLS working group session. It was a similar draft for the option 2 with two separate certificate chains that are both used for authentication. And from my understanding, it was strong opposition from the audience for this kind of solution because of the complexity. And I think that many people prefer combined certificates.
Yeah, but I don't think there's a conclusion there that.
Okay, it's just.
I just want to use a single solution for both.
Tirunokia. I mean, just to add to what Valerie was saying, right? I mean, it's good to have 2 options, right? LAMPS working group has 2 approaches. Basically, they talk about scenarios deploying dual certs, right, where they have 1 cert linking to another, which is for offline use cases, not for protocols, because anyway both the certs are sent in the same payload, right? And then the composite ones, right? So at least LAMPS has produced both sets of documents. I think the migration strategy has to be figured out in protocols in the sense that do we want to support both approaches or one of them, or let deployments pick what they want to do, right? So that's probably an open question that's not yet been decided or concluded in any of the working groups so far.
Yeah, I think at least right now, I don't think the industry has made the decision which one to go, but at least in the IETF, I think both there's parties for support either of those options, and I suspect that there will be CAs choosing either of those approaches. And as an application, IPSEC as an application, we rely on the PKI infrastructure, which is CA. We have to, in my mind, we have to support both.
I think we need to move this discussion to the list because we are running out of time. We are already 15 minutes late, so.
Okay, thank you.
All right, next one.
Hi, I'm from NTT Communications. I'm Fukagawa, and my presentation is about post-quantum hybrid key exchange with N2 in the IKEV2. First, N2 stands for nth degree truncated polynomial ring units, and that is lattice-based PQ-CAM, and that is fast encryption and decryption with relatively small key size compared to other PQ algorithms. And N2 has long history, and also N2 is patent-free. And the security level and the performance is under discussion in the CFRG. And my draft and my motivation is, I have two motivations. One is that in use case that requires high security, there is a demand for PQ-CAMs support in the IKEV2. And also, we have standardization because we implement concrete implementations and have some interoperability as other network devices. And also, depending on requirements, we welcome the cryptographic agility. That is why I propose the N2 algorithm in the IKV2. And here is related works, and I focused on these three works. And the first is that RC 9370, and that is a multiple key exchange method in the IKV2 protocol. And in the earlier section, there is a issue, but that is a problem of infrastructure. So we will follow up that improvements. And also there are two proposals about the PQ algorithm, PQ CAMs. One is ML CAM, that is a Kyber, and that is a NIST selected algorithm. And Panos and Gerardo are writing the draft about implementing MMCAM into the IKV2. And also there is a fraud CAM that is also CAM protocol, and that is supported by LWE program, and Greeding one is writing the draft. And what is N2? We are discussing the N2's security and performance in CFRG research group, but the key point is that I think N2 is sufficiently meets the requirements as an alternative PQ algorithm. And we request the assignment of CAM number, CAM ID in to IANA. Yeah, and we have 5 parameters in N2. And that is an example of running hybrid CAMs in N2. And first, IKE SA init exchange state, we negotiate about the, how can I say, the capability of adding some another CAMs, and then we choose N2 algorithm. And implementations, N2 algorithm itself is currently deployed in Bouncy Castle, and DeepOQS is maybe supported soon, and also N2 algorithm as a CAM in the IKV2 Strongest one will be supported soon because libOQS is currently working on the entry algorithm. And also we have some software routers that support IPsec VPN, and that will supported soon as well. And next steps, we think it's ready for working group adoption call. And also we will conduct some public side meeting tomorrow 10:30 to 11 o'clock in Segovia room. So please welcome to the public meeting. And also we welcome your feedback and comments to improve this draft. And feel free to join our works. Thanks. Any questions?
I think we are going to be skipping questions and take them to the list because otherwise we are not going to be able to make the two other presentations we have left. Okay. So let's move to the next one. And so if you have any comments or questions about this, take it to the list.
Okay. So, thank you.
Okay, hello everyone. I'm Liang Xia from Huawei. This is a 00 new draft. It's no 01. Okay, it's about the actually it's following the current ESP work, and we want to define performance improving mechanism for the IPsec ESP packet. And basically, firstly, I like to explain what is stateless encryption means here. Here, the stateless encryption means that only one group key or master key here, and we use this kind of key to perform the KDF to get the every session key when the packet arrives. So, and this can help us to skip the IKE key negotiation. And to explain why we need this kind of mechanism, here in this draft we provide 4 use cases, and also together we have the 2 existing industry stateless encryption schema. And so by introducing this use case and the existing schema, and we abstract the requirements, and in the future we want in this draft to propose general and flexible stateless encryption schema for the IPsec ESP. So the 4 use cases include the very general computing, the CS model of general computing network. The second one is the cluster communication of the high performance computing network. The third one is NIC or DPU pool of the general computing network. The fourth one is the AI computing network. So you can see this covers most of the current network that's widely in the industry. And the existing in the industry stateless encryption schemas include the Google PSP and the UEC, Ultra Ethernet Consortium's TSS transport security sublayer mechanism. And by this use case and the industry implementation, we abstract some basic requirement about this stateless encryption, about the group key. In short, we need a group key, and we need a very high-level security group key. And based on this group key, we want to achieve the very flexible and fine-grained security session key duration. And in some case, we need some stateless encryption proxy to help us to do the end-to-end IPsec session across the trusted domain. Okay, so finally, we want to emphasize that, of course, we need a very precise or widely consensus definition of what is stateless encryption. Actually, I'm wrong from the very beginning. Actually, there's definitely no totally stateless. Here, this means that maybe the minimum security state or the less security state comparing to the current IPsec protocol, definitely not totally stateless. Okay, so because the time is very limited, so I will quickly go through these 4 use cases. The first one is, as I said, is a client-server model of the general computing network. So the biggest problem here is that in the server side, its hardware memory cannot save so massive security context session information. So the Google PSP proposed their solution to use the master key in the server side, and the server side do the key derivation. So it doesn't need to save so massive session key. But in the client side, it also need an out-of-band channel from the server to the client to forward or to transmit the every session key to the client. So in which way Google PSP solution can save half of the security session. That is from the client side to the server side it can save, but from the server side to client side it cannot save. So this is one improvement. And the second use case is in the HPC network. In HPC network, there's let me say that there are m computation jobs, and every computation jobs include n instance of computing instance. So by plus them together and distributed all these job instances to the different servers, actually we may have a m plus n connection between every instance of every instance of one job, okay? And then if we have m jobs, so we have plus n, okay? So which means that there may be also maybe a large number of the IPsec session among these instances. So we want to save the IKE simplify the IKE negotiation or save the IKE negotiation and do the session key negotiation or derivation very quickly or very flexibly. So you can see in the right side is a UEC TSA solution. Actually, they define a group key, and this group key is shared among all the instance of one job. And with this way, we can do the key derivation based on the group key and some context together with the packet. So we can we do not need to depend on the IKE to do the so many point-to-point end-to-end key negotiation. And the use case third one is the NIC and DPU pool of the general computing. And there are two sub-use cases. The left one is very similar like my use case one. Actually, you can consider the NIC as a pool. And it's like in my use case, it's like the server side. So the older client want to access the VM behind the NIC, and the older NIC are considered as one pool, and they should provide the same security session to the client for the one VM connection. Okay, so how to if we use the traditional IKE mechanism, which means that because they should have the same session key, so the client needs to negotiate with every NIC. Then the NIC among themselves, they should synchronize the session key to make them, make them consistent. So that is very complex. But if they have shared the same group key, so they can use the same group key and the same context and do the computation during when the packet arrives. So it can skip the IKE negotiation. And the right case is we have the two sides. We have both have the NIC pool, and they want to support the east-west traffic in the data center. So the same situation is here. If we don't have a group key shared among the trusted domain, so we need the point-to-point, one-to-one key negotiation. That's very complex. And the last one is easy to understand. This is a very typical AI data center scenario. Usually we have a computing task. This computing task can be distributed among several distributed data center and among the CPU, NPU, and the DPU, all the XPU. So how can I construct a security connection among this very dynamic XPU and also save the provide a simplified way to set up the connection among them. We think that maybe this time the IKE is too complex for this. So we wanted the group key to help us. Okay, so I give the very short summary here. Why we need group key? Because if we don't have it, for every end-to-end connection, we need to the key negotiation, and it will introduce latency, and it will introduce more delay, and also like I said in the use case 1, sometimes our hardware memories cannot save so many security sessions. But with the group key, there's also introduced some extra or some additional risk. If we have this group key, though this group key if it's compromised, the whole group, session key is compromised. So how we guarantee this group key be secure enough? This is something we need to develop. And another case is that even we have the group key, but we want to provide a very fine-grade session key. So we not only have the group key, we also have the context. If we have defined the context carefully and flexibly, we can provide this fine-grade key session key isolation. So okay, so I think this page just for your reference. This is an industry 2 mainstream implementation for the cloud or for the AI data center. So the color I emphasize here is how they do the curation and how they do the key update, how whether they support the flexibility like the crypto offset. So because of time limit, I don't go into details. So finally, I have 2 pages of the requirement summary. The first page is about the group key. So how we define, how we use, we need this group key. And with this group key, we need some mechanism to guarantee security. And we also need some mechanism to do the key rotation, to update the root key. Okay, this is pages mainly about the group key. And second page is mainly about the session key. So we need a very high speed KDF and very secure KDF. And we also need to define the context mechanism, so to support the very fine-grade session key isolation. And we also need some time. For example, we can include the epoch in the context, so which can facilitate the data key very quickly without the group key update. And last point is that, like I said, some across chapter domain scenario, we may need this encryption proxy capabilities between the 2 chapter domain. So because this is very initial version, we just listed the use case and the requirements. So that's all. And yeah, you have any question or comments?
I think we take the comments under the list again because we are running out of time. So, all right, so let's go to the last presentation. And you have about 5 to 6 minutes.
Last but not least. Okay, Jack the Nimble, Jack the Quick. A few of the previous presentations pointed out difficulties and some potential solutions for the pains of signatures and ICE-auth. Old wisdom says, doctor, it hurts when I do this. Don't do this. So we are offering a different authentication method that does not rely on dynamic signatures. That is formally proven and frankly, cryptographically more beautiful than the current approach. So we are proposing minimalistic, and you probably heard me saying that already, authenticated key exchange. It's, again, it's formally proven, it's compact, this and that. I'm sure you can read faster than I talk. It is beneficial in constrained environment, but if your environment is unconstrained, but you have a server with a great many clients, then for each client, it may not matter all that much how many bytes it needs to send over the wire or how many seconds it takes. But for a server who needs to handle great many of those, every extra byte it needs to process and every extra computation second is something that is taken from that server's primary functionality, primary mission. So the applicable use case are not only constrained environments. Also, it is worth mentioning that since we avoid explicit digital signatures, we may be able to use signatures in certificates that otherwise may be unacceptable. For example, Falcon is more compact than MLDSA, but it has a disadvantage. Its implementation is hard to validate. But that applies mostly to the signing part. So if you need to deploy only a verification part, you will be better. The logic of the protocol is very straightforward. You perform ephemeral key encapsulation to establish a secure channel, and you preserve this for the future key derivation. You exchange your certificates, or as Valerie suggested, if you have an option, you exchange key references that would save on the amount of bytes across the wire considerably. You validate certificates, you perform 2 chems, encapsulate, decapsulate for authentication purpose, you derive your share secret through KDF, and specifically what KDF is for the working group to decide. And lastly, you do key confirmation. All the big and small things that this protocol does turned out necessary for the formal proofs to hold. This is not relevant here. This is not relevant here. This may. Against using MLDSA, you would have significant saving in both bytes over the wire and computations. But again, since the slides will be available, you'll be able to view it at your convenience later. For now, just take me on faith that it is better. As the next steps, we would like to incorporate this protocol into all of these. We understand that a working group would require something more specific than a protocol definition. So we are working on specific internet drafts for each of those 3 working groups. But in the meanwhile, it would be nice to gauge acceptance and get the vibes from the group. Like if the detailed RFC is good, would it be acceptable? And that is pretty much all I wanted to say.
All right. So I think we will take discussion about this also in the list because we have -1 second. Just run out of time. But anyway, so I think that's all. Shall we take all of this discussion to the list? I think there is several documents that we would like to get an adoption calls, and there's few documents that want to get a working group. Actually, yes, adoption calls are the only one. We don't have a working group last calls yet. But anyway, so people who are thinking that documents are ready for the working group last call, adoption call, send an email to the mailing list and, list your documents so we don't forget because there was a little bit, we had a little bit of time constraints here. So I think that's everything from the IPSECME that I have. Do you have anything?
And Tero, thank you for accommodating us. And a question to you and to everybody. Would it make sense to ask for pseudo adoption of this?
I think that the protocol, I think we need to have actual protocol, but actually one of the things is, the question is also, do we actually want to do this in EAP or do we actually want to do it as a specific question? But this is question for the list, I think. All right, that's everything. See you probably next time.
Thank you all.
So good. Last is CFRG.